Hello everyone. I will be continuing on from my last video. I had a previous recording, but I got interrupted in the middle of it and I don't like to edit. And so I just thought I will keep what I already have in the same document and then just re-walk you guys through why I did what and why you should do that. Okay, so first things first, I'm going to draw some attention to is this part right here. I'm not really so like pushy on subscribing and liking, but I've appreciated your guys' support thus far. However, 92 to 8 is absolutely ridiculous. So please, we are trying to take more so of the 92 and put them in the 8% bracket. So if you don't mind contributing, I can help more people as a result of it. And that's really the goal of this YouTube channel. Okay, so starting off with problem 1, I initially outlined that they're looking for the largest interval and they're looking for the interval such that it guarantees a unique solution, okay? And first thing that you do when you sort of see a problem like this, you're looking for an interval, and the only way that you can really start to narrow out your options is if you understand what fits and what doesn't in that interval. And so when you do this question, okay, you're going to have to get the largest order magnitude derivative and isolate that. And so factor out anything that's next to it. And that's exactly what we did for A. So we took that x minus 10 and we brought it down here. We factor, we also brought it down over here. So we know that we can't have x equals 10 and we can't have x equals negative 7. And so and remember that these brackets, they represent exclusive boundaries and these square ones are inclusive. So after we do that, we have 3 main intervals that satisfy or supposedly satisfy our question. And we know, I'll tell you how to narrow it down. So we have negative infinity to negative 7. We have negative 7 to 10, and these are all exclusive, just so we're clear. And we have 10 to infinity, okay? Now, the first and the third interval are much larger than the second, but there's a reason why we chose the second. And that's because they're telling us that in our initial values, y at 0 equals x, y, and 4, 7, and 8, and at each of those at their respective derivative. So if I choose this interval, right, it's larger than the second one, but that doesn't contain my solution at y equals 0, or y prime at 0, or y double prime at 0, nor does this one. And so process of elimination, we got to the middle one. But basically, when you do this question, just look for which interval is largest such that it contains my solution. Or even vice versa, because you could have possibly 2 intervals, but one doesn't contain your initial value, right? So yeah, be wary of that. And then the second one, I followed it. I didn't do the full process, but I followed the same structure. So the only difference is that you have, instead of this negative, it goes to a positive. And so now we just have x cannot equal negative 10 and x cannot equal negative 7. We get down to these 3 intervals, okay? And we're really just looking for one that contains our solutions at y equals 0. So this one doesn't because it's capped at negative 10. This one doesn't because it's capped at negative 7. And this one does. And that was our solution. Cool. So continuing to the second one, we're asked which of the following sets are linearly independent. So when you see linearly independent on whatever interval, you have 2 ways of going about it. You have Wronskian and you have the superposition principle, okay? Now, Wronskian, or not so much, I'll put it more so in linear algebra terms. I just don't like linear algebra because it's a lot of math theory and too much like stupid ass words. So I'm going to put it to you guys like this. When you take the determinant of whatever matrix, linear independence exists if that determinant doesn't equal 0. And when you do the superposition principle, okay, kind of like in linear algebra, for linear independence, you cannot create scalar multiples such that it equals 0. You cannot do that. You'll have linear independence if you can do that, okay? So you'll have linear independence. I just want to make sure I said that. Okay. So with that being said, and you'll know when to use what based on like the functions, how they look like. So the difference from the first to the second, and you'll see why I didn't use what's it called? You'll see why I didn't use the wrong skin in the second one, is because all of these are exponential functions, right? I'm not gonna have huge derivatives, right? Because they're nice numbers, but I won't get a line of zeros. The first one, however, I will. I get 5x, I get 5, and then I get 0. That's really nice. The more zeros I have, the better, and so then I just take the determinant along 2, so across these out, and you guys know how to do that. Get down to 90, which doesn't equal 0, so the first one is linearly independent. Cool. Now, the second one is, we use superposition principle for, okay? And so I put all my functions out, and then I distribute the C3 in with a 1 over 4, and then I just reorganize. Don't worry so much about this view. Like you can go into depth and solve all of them, but I didn't think that was necessary. If you look at them, okay, you'll see that you want to get rid of all of these. That's your goal, to see if you can find C1 such that it equals 0. Okay. So C3 is the common one between the two. One has a negative, one doesn't. Starting with C1, I want to get rid of this. So I'm looking for some number C3 that's negative that I can put into, divide by 4, and multiply C1 such that it gets rid of each other. And the number for that, I think I wrote it down somewhere. Where did I write it down? Okay, I don't think I write it down, but I'll write it down now. So if you plug in C1 equals 2, C3 equals negative 40, and C2 equals negative 5, then you'll get that. So what you'll get here is just in a different color. You'll get 10, right? You'll get negative 10, you'll get negative 10, and you'll get positive 10, because the negative, when you multiply it with the, with this negative, it'll become positive, and etc., etc. Okay, so we know that there's scalar multiples of numbers that when I put it in, it will be equal to 0. So it is not linearly independent. Now moving on to the third one, okay? The third one I took the wrong skin of because I saw the 2, and that was my first instinct. I'm just like, okay, I'm going to get zeros. It won't be so bad. Multiply it out, it looks like a mess. And now, maybe if you plug in a bunch of like trig identities, then you can get this down to a nice number. But I didn't want to, and so linear independence is for this. There shouldn't be any values that when I plug it into after taking the determinant, and when I took it here, like that's the determinant. That's it. I just have to simplify it. There shouldn't be any numbers in the entire interval that will get it to equal 0. It's just that simple. So like something like e to the x equals 0, right? From negative infinity to infinity with real numbers, then you got nothing that you can put into there that will get it to equal 0. Absolutely nothing. Okay? So that is linearly independent. Now for this case, I'm like, okay, I have all these really like wacky what's it called? Formulas. Let me get rid of these. Oh. Yeah. So I have all these really like wacky formulas up. What do I do with them? So I'm like, okay, if it has to be linearly independent for every number, then if I plug in 0, it should also be linearly independent. It should not equal 0. The determinant should not equal 0. But look what happens when I do that. I put it in here. This is multiplied, by the way. I put in the 0 there. I'm going to get 0 out of that. This whole first term goes away. I put in the 0 there, sine of 0 equals 0. This whole first term's away. You have 2 times 0 equals 0. It's not linearly independent. It's that simple. Okay. The third question I saw a lot of questions on in the group chat, and so I'm going to try and cover this in a way that... well, I already covered it, but just kind of reviewing in a good amount of context. So, fundamental set of solutions. There's 2 different ways to go about this problem, okay? Now, the second way is really, really, it saves you a lot of time, but you can't use it in all use cases, but it works for this question. You just have to be willing to recognize what equations you're working with, non-homogeneous or homogeneous, and you can work accordingly. So these are homogeneous functions. The third one, you can look at it and say, well, that's not homogeneous, but its solutions are. Okay? And that's what I'm really worried about here. I don't want anything crazy going on in the solutions. And so the second one I'm gonna explain briefly afterwards, not actually doing it because I'm gonna get to the same solution regardless. But yeah. So let's just get on with it. Now, if I want a fundamental set of solutions, okay, and they're saying that these two functions, right, they're proposing that these two are solutions, and they're saying, like, can I get a fundamental set of solutions from those two? That's what the question's asking. So, I'm going to use my superposition principle, basically stating that for any y, if I have a scalar multiple of two other solutions, then adding them together will also equal a solution. Cool. So, with these questions, you're using your auxiliary. I'm just going to use characteristic equation from now on because it sounds nicer. So, I'm going to use my characteristic equation, and I factor that. I get m equals 3 and m equals 9. The c's I'm not so worried about because those are just scalars, right? And so I drew the relationship between the 4 and the 5 translating down to here. And then the m's are exactly what I need them. I have 9 and 3. And if you want that in really summed up, boiled down terms, after you factor your characteristic equation, if the factors of that are the exponents next to the x's, you're good. So it does form, okay? Going to the second one, and the reason why I wrote these one is this is distinct real roots, this is repeated real roots, and this is complex roots, okay? Or sorry, two distinct real roots. So the second one, I have one real root with a multiplicity of 2, which is just a repeated root, it's just squared, like we put right here. And we go back to the characteristic equation, but we find that, and you guys can correct me if I'm wrong, but if I try and use the base characteristic equation, right, and I'm proposing the same solution, like I put in just like it's just 1x here. It's just 1x here, same as how it was, same as how it is over here. Then I'm saying that this only has one solution. Let's just say it's y prime equals x. That's what I'm saying this is at that point, which is incorrect. This is a second order. I need two solutions. And so I basically just add an x alongside to this, and everything ends up working out. And that's all you really need to know. Just when you have the repeated one, you take the original one and add an x next to it. Okay? So, with that being said, I look at what I got right here, and then I draw comparisons to the proposed ones. I'm like, okay, they're both to the 1x, cool. This one has an x next to it. And the numbers I don't care about. This is also good. Now the third one, okay, you, yes, can go into the nitty gritty of everything, but there's like, and you'll get down to here and realize that it'll never equal 0, and that ends up working for our case. But I wanted to kind of leave off right before I got to the actual like most correct way to do it, because you guys want a structured format to this at the end of the day. Okay. Oh, why did I add a paper there? I want a paper here. Okay. So we have our auxiliary, or we have our characteristic equation, and I'm going to go back and rewrite our equation. I'm going to give this a nice orange. So my equation is this: x squared times y double prime minus 6x times y prime plus 12y equals 60 over x. Cool. Now, I'm proposing a solution to this, and the solutions that I'm proposing is x to the m. You guys can review your lectures as to why it is that exactly, but you can also listen to me and just say it is that. Okay? This is y prime, and y double prime would be m times m minus 1 x to the m minus 2. And plug it into the equation and see what you get. So I'm gonna do full process for this, because this one is pretty. This is the second time I see a question like this, and they like to fuck around and find out. Okay, and that's that. So I have x to the m times x squared minus 6x times mx to the m minus 1 and plus 12x to the m. Cool. So the most important thing that you have to recognize when doing this is the x squared and the x to the m minus 2. I don't know why it visually looks weird sometimes, but just please recognize that you can redistribute this and make your life a whole lot easier. So continuing on, we get, this is all like, and you realize, like when I distribute this over here and distribute this over here, right? I just get x to the m, which is what I'm looking for. So, and then I end up redistributing this x to the m over here, and you'll see what happens. I'm going to skip in terms of the distribution part, but you can work on that on your own and see that it's the same thing, because we have a lot to get to here, and I need to show you, or at least mention, the other way of solving this. Okay, cool. So then I factor out x to the m. I get m squared minus 7m plus 12 equals 0. I factor this, and I'm going to get m equals 3 and 4, and x to the m equals 0. No solution, because you can't ln 0. So I have m equals 3 to 4. I look back at my question. I see that the exponents are that, and so we're good. So this is also forms of fundamental solutions. And so the answer is E, all of them. Now, I'm not going to go through all of them, but I'm going to pull up the work that I had previously done on this, and it also proves true. So just give me 1 second. Okay. If I want a fundamental set of solutions, then when I take these two solutions, okay, when I take the proposed solutions right here, then I should also have from those two solutions, a determinant which is non-zero. Okay? Because my fundamental set of solutions should be all-encompassing. You shouldn't be able to, it should be unique, right? So every solution should be unique in that sense. I shouldn't have repeated solutions. Now, if that's the case, then when I take the determinant of the, when I take the Wronskian of these, then that's exactly what I'm finding out. And so if my Wronskian is non-zero, okay, then I have a fundamental set of solutions. And so what I did here, and it's on from negative infinity to infinity, what I did, and I'll classify this as method 2, okay, is if we take the determinant, for the first one we'll get negative 120 e to the 12x. Okay, for the second one, we'll get 14 e to the 2x. And for the third one, okay, now, my range is exclusive. So it's the same for the first and the second one, right? But when I come to the third one, and this is where you guys need to focus a little bit. When I come to the third one, the 0 is not included. So if the 0 is exclusive, right? If I put in any number for this x right here, there's no way it equals 0. So the first two are good. Second one, this 0 is exclusive. That means there's nothing else that makes this third one 0. It's also good. And so you get to the same answer. I think personally you're doing a lot less work than trying to factor in this. Maybe for the first two, just go about it the normal way. But the third one, you can definitely save yourself some time in just approaching it with that Wronskian way. Okay, cool. So that's the third question. Let's go to the fourth one. Two parameters corresponding non-homogeneous. Okay, so there's a very key word we have to read here, which is non-homogeneous. And they're saying it's a two-parameter family. Is a given two-parameter family of functions the general solution? Okay, so how do you read this? And I'm going to pull up some of my previous work to this. That way we're all on the same page here. I don't think this question was so bad, but regardless, I want to make sure that I'm giving you guys the best. Okay. So for the fourth one, right, I am looking for, let me make sure I pull up, because I don't have the answers along with me, but I want to make sure I'm giving it to you right. For the fourth one, it's basically asking me, like, okay, I am going to make my characteristic equation, and I need to figure out, is the proposed general solution actually what it says to be? So how do I figure it out? The general solution is y equals the complementary solution plus the particular solution. Okay, so the complementary for the first one is that, and the particular is this. Complementary, particular, complementary, particular. It's the same thing, okay? Now, for the first one, and you'll notice that the equations, right, are the exact same as part 3. Okay, cool. So that makes our life a lot easier. And you'll also know that because of that, I'm going to have 3 different cases. I'm going to have the distinct, I'm not going to write it down, but I'm going to have the distinct roots, I'm going to have the repeated roots, and then I'm also going to have the complex roots. Okay? So really understanding this formula, we can now approach this question and see what we're looking for. Okay. So the first one, after I factor it, because we already have them, we get m equals 3 and m equals 9. Okay? Instantly, just off that, I don't have to do any more work knowing that this can't be the general solution because my exponents are not the same. I don't care. I don't have to do any more work than that. Exponents are not the same. Instantly is not the general solution. Because this is how we solve for the general solution. We're just, the question's asking us, just confirm it, right? Because we have to confirm it to verify our answer. And if we go to the second one, okay, so this is the first one. This question really is not like anything crazy. We go to the second portion of it. And let me see what I ended up doing here again. Okay. So, yeah, I actually won't even, I can't find where I wrote my solution for this, but I'm just I know that like m equals 1 for this from the past question, right? So how do I have 4 here? That doesn't make sense. This y particular needs more work, but I don't need to go there because the initial proposed complementary solution is not correct. Now, the third one, okay, we already solved for what m should equal, right? We already solved for what m is. And m, from our previous question, was 3 and 4. So how is it 5 and 4 here? So the question, my answer was F, which is none of them. And this question I got the first time around because it wasn't so bad. Okay, on to the fifth question. And I'm sorry if I'm rushing ahead of things, but I have a I don't wanna under how do I delete this page? I don't want to cut the quality of the video, but I also want to make sure that you guys are getting the point across. And if you need more time, just really think about what I'm saying, and you'll be just fine. This question took me a couple tries, I won't lie, but eventually I got down to it. So they actually have this exact same. This is how I start to piece the solution together. They have this exact equation in the lectures. So I recognize that. I went to the lectures, and then I start to see, okay, what do I need here? Okay, so yeah, I even had it written out before. Okay, so for this question, right, they're saying that our general solution, right, which, so we're clear here, and this was superposition part 2, which is the place in the slides where you'll find it. Our general solution, okay, for L at y equals g1 at x plus g2 at x, okay? And this goes saying with accordance to y at this particular solution, okay? And I'm just rewriting the lecture notes right now, but just bear with me. Equals lyp plus ly squiggly equals g1 plus g2 equals g, which also equals a particular solution. Okay? So with that being said, given that we don't know what the order or how the differential equation actually is described here, but we know that this is like the differential equation that models it. So I don't know the order of it, but I know that this is what describes it, okay? And you'll see here, if you kind of recognize the pattern, is that I have solutions here that are really, really close to this. It's like if I multiply by like a certain number, I'll get exactly what I need. Okay. So with that being said, let's get straight to it. Now, if my equation is L at y equals 10e to the 3x cos x plus 7x e to the 3x, okay? And we know that that this is L at y. This is going to be huge. This right here is going to be huge in getting to our answer later down the line. Okay. So I need what's inside right here. So you guys are gonna have to bear with me on this one, because this might be a little bit weird to understand, but when I start getting through the process, you'll see why it makes sense. So if I multiply the g1, let's just call it, by some scalar number, then I could get it in a way that resembles, if I multiply g2, I'm just going to start with g2 because I have it written down like that in my notes, but g2 by some number, I can get it in this format. So what would that be? If I multiply, and I might as well also do the second one as well. For cos x, e to the cos x, I need a 12 in front of it, okay? So what I can do is I can multiply them by 1. No one says anything against that. I've changed nothing from the original equation, but now I'm just going to change the order in which they're multiplied. You guys are going to see how crazy this is. Times 12e3x cos x plus 7 over 10 times 10x e to the 3x, and yeah. Okay. So cool. Now we got it in our ly at x, okay? And there's a reason why I wrote this out, and you'll see why. So this now equals 10 over 12 L at y1 plus 7 over 10 L, let me just put it like this, L at y3, okay? And, hold on. I messed up the notation. L at y3, and this is at y1, if I'm correct, right? Yeah, y1 and then y3. Okay, cool. And they gotta give me like a shortcut button to add a page. They really gotta give me a shortcut button. Okay, cool. So if that's the case, and we know that this equals whoops, and this equals L at Y, and we're gonna try and correlate it to this, then really, okay, Y equals 10 over 12 Y3 plus 7 over 10 Y1. And this is my particular solution. Because my solutions to this equation are particular solutions, okay? And it works the same way. If this being added together inside the bracket, right? And what I could do here, I'll do an intermediate step just so nothing is lost, okay? What I could do is factor out the L, literally. So 10 over 12 Y3 plus 7 over 10 Y1. And look at how crazy that is. Because now it's really clear that Y equals this. And Y is my particular solution. And so you just expand, and they give you Y3, right? They give you Y3, they give you Y1. You just expand those out, and that's your answer. Cool. Okay. So now, 6 and beyond is, and I only got until 9 confidently. Okay? So some person in the group chat sent what I believe 10 is. I'm going to try. We're gonna try and figure out 10 together, and what's it called? I'm gonna try and figure out 10 together with that guy, with what that guy said. But I'm like not. I don't like to use other people's solutions because I don't know where the hell they got it from or how they got to it. So I honestly might just leave this up until now. Without further ado, let's get through 6. Okay. So we have initial value problem. Okay. We're gonna get straight to classifying it. Okay. And to classify it, we're going to have to do a couple things. Okay, so let's factor this, right? Because we have a second order. This is homogeneous, so it's second order homogeneous. Let's factor it. That's what we have to do. Get used to doing to solving these things. So if you factor it, okay, you'll get m minus 7 plus 8i. M minus 7 minus 8i equals 0. So what is this? You have a repeated, and you have to classify, you have to understand how to classify these problems. Repeated complex root. Okay? And so the general formula for a complex roots is e to the alpha x times cos to the beta x plus sine to the beta x. Okay? And so we know, damn, why I feel like I'm writing massive? Okay, damn. So we know that m equals alpha plus beta I, and in our case this equals 7 plus or minus 8i. Okay, so sorry, and I forgot the C1 and C2. This is very important. Okay, and so we're just going to start plugging in what we know. So e to the 7x times C1 cos bx, which would be 8x, plus C2 sine 8x. Okay, and we're going to now use our initial values to solve. So I have 4 equals, the e to the 7 times 0 goes away, it's just 1. And the cos at 0 is 1, so I get C1, okay? And then I put the 0 in here, and I get 0, of course. So the C2 goes away. So instantly, I know that C1 equals 4. Cool. So now I take the derivative of this, okay? Equals 7e to the 7x times, multiply by the second. Oh. Okay. And then we will add the derivative of the second. So C1 is a constant, but I get negative 8 c1 times sine 8x plus c2 plus 8 c2 cos 8x. Cool. And our second one says that y prime at 0 equals 3, and you have to do this. And for these initial value problems, you'll notice that over and over and over again, you'll get the initial values, and then you have to use these to solve for c. So if you're not solving for c in your process, you know something's up. Okay, so then we get 3 equals, we have 7 now, times, so the first one would be c1, because the 8 becomes the cos of 0 is 1, plus the second one goes away, plus this sign goes away, 8c2. Cool. So, and that's really all we got here. So I can actually get rid of the brackets just to not confuse you guys. So I get 3 equals 7 times 4 is 28 plus 8c2. And so I get c2 equals negative 25 over 8. Now, not going to, but you just plug the c1 and c2 respectively. I'll put it here, plug it back in there, and then you're all good to go. Okay, let's move on to the 7th. So this one, we already know, we've already factored this a few times now, and so we know that we're going to get something like m minus 1 squared equals 0. Okay. Now, in this case, we have a repeated real root. Okay. And so we're gonna follow kind of along the same course. So our general, our complementary solution to this equals c1 times e to the mx plus c2 times x e to the mx. And you'll notice here, I really like this question because you'll notice here that they don't give you the y prime. And that's for a reason, because you don't actually need it, which is the crazy part. So, okay. And we know that m in our scenario for both of these is 1. Okay? So, with that, we know that 1 equals c1. That's literally it. As soon as you plug it in. And we take the derivative, equals c1 times e to the x plus c2 times e to the x plus c2 times x e to the x. Cool? Okay. So yeah, we'll just keep going from there. So now we're going to plug in the initial conditions. So we get 6 equals c1 plus c2. And this is at 0. Oh, no, this is at 1. My bad. Gotta be careful. So 6 equals c1 times e to the 1 plus c2 times e to the 1 plus c2 times e to the 1. So we get, hold on. Something's up here, guys. I'm going to continue solving here, but I know something's wrong. Because I'm going to get 1 plus 2 c2, right? So 2e c2. So I get, oh no, this is times e to the 1. So then I get 6 minus e over 2e equals c2. Okay. That was my first submission, I think. Yeah, that was my first submission. And that is definitely not correct. Because I know it's not correct. I checked it, that's why. So, for this, okay, let me, yeah. Oh, was I retarded and I didn't plug something in? Hold on, I'm just reviewing my work here, guys. So, c2e to the x, that's perfectly cool. Okay. Then I take the derivative. I think I might have just manipulated something wrong. Let me check my work again. So c1 times e to the x plus the derivative of x, so you just get e to the x, plus the derivative of e to the x, which is just e to the x, times x. And so, oh, wait. Hold on a second. Yeah, so the first one I plug in 0 and I get 1. That's perfectly fine. The second one, when I plug in 1, okay, and I get 6, then what's happening is I get C2e plus C2. That looks about right. What did I change here? E to the x. I just take the derivative wrong? Because look, I'm looking at my work right now, and I'm looking at what I did right here. And I'm trying to remember what brought me to do what I did on when I initially did it. Because I put in the right answer, but it's been a little bit of time since I did this question. Okay, let's see. So I proposed my solution of e to the x, and it's a repeated real root. And so I have e to the x. No, you gotta have that. You get C2. Yeah, I'm not too sure because I took the wait. Oh, I'm retarded. Oh, I'm actually so dumb. I didn't. Oh my god. I literally told you guys at the beginning of the question to look out for this. Okay. So, yeah, so I don't need to take the derivative because I literally outlined it right here that you don't need to. My bad, guys. So you get 6 equals e to the 1 plus c2 times e to the 1. So you get 6 minus e over e equals c2. And this is the correct one. So yeah, I didn't clock it in. I also haven't had coffee yet, so mind that. But yeah, that is question 7. And let's move on to question 8. So this is to classify it, a third order. That's really weird. Order differential equation. And this is homogeneous. Okay. Cool. So if we factor it, we'll get m plus 3, m minus 8 squared equals 0. And so we get m equals negative 3 and m equals 8. Cool. And we know our initial values. So there's going to be a good amount of work to be done for this question. And we're just going to get straight into it. So I'm going to propose my solution here, which is y equals... Oh, sorry. My complementary solution equals c1 times e to the negative 3x plus c2 times e to the 8x plus c2 times plus c3 times x e to the 8x. Okay, cool. And we know why we have to do that because of the repeated root. These are some things you're just gonna have to pick up over time. And so this is my complementary, and I didn't really clock it when I first wrote that down, but this is the general solution to it. Okay, so we're gonna keep solving for our values. So at 0, okay, I have c1 plus c2, and so c1 just equals negative c2, which is amazing. If I take the derivative, which I actually have to this time, then I get negative 3 c1 times e to the negative 3x plus 8c2 times e to the 8x plus c3 times e to the 8x plus c3e to the 8x times x. Oh, and I have to be careful of that. 8x, right? Okay, cool. So now I plug in 0 again. I get negative 3c1 plus 8c2 plus c3, and then the last one goes away. Okay, and what I'm going to do this time around, I don't really have to at this point, because even if I did plug it in, even if I did plug in c1 here, right, then I still have c3 to worry about. So we're just going to keep going to the final derivative, and this is 9c1 times e to the negative 3x plus 64c2 times e to the 8x plus 8c3 times e to the 8x plus 8c3 times e to the 8x plus 64c3 e to the 8x. I have a paper here. Okay, cool. So, with that being said, if I plug in 0 again, I'll get 0 equals 9c1 plus 64c2 plus 16c3. Now my c3 equals 3c1 minus 8c2. And now we can begin to, oh, hold on. So I'm going to get 3, this is not 0, going to get 3c1, right? And now at this point, what I could start doing is manipulating and kind of looking at my differential equations. So I'm going to have this one labeled as 1, okay? This one labeled as 2, this one labeled as 3, and we're going to keep going from there. So what I could do is, because I see C1 and C2 here, and I can isolate for C3 really easily in the second one. So I'm going to say C3 equals 3C1 minus 8C2. 3 equals negative 9C2 plus 64C2 minus 48C1 minus 128C2. Cool. Okay. And now, since we know that C1, okay, C1 equals negative C2 from equation number 1, I'm going to sub that in and then simplify really quickly. So I'm going to get 3 equals negative 121 C2, and C2 equals negative 3 over 121. And if C1 equals negative C2, then C1 equals 3 over 121, and C3 equals 9 over 121 plus 24 over 121 equals 3 over 11. And when you plug those in, that is the correct answer. And I solve for C3 from this equation. Okay, awesome. Yeah. Okay, so let's keep going. And we are now on to question number 9, which I think was a pain in my ass. But most of these questions are anyway, so it doesn't really matter. Okay, so this is a question that initially when I looked at it, I was like, what the fuck is going on here? But when you take time to look at it, it's not so bad. Okay. Sorry, I'm just stretching, guys. Takes a little. Okay. So, we have a second order differential equation here. When I factor it, I'm going to get m minus 4 and m minus 6. Okay? And I see here that this is, we call this f or g, but essentially this is my yp. This is my particular solution, okay? And I know that y equals yc plus yp. Now you might beg to ask the question, why didn't we use that on the previous ones? Well, they're all 0. So when you see something on the right side of the equation, it's usually a good indicator that you're either using undetermined coefficient method of solving the differential equation, or you're using variation of parameters. Okay, cool. So with that being said, we have our yc, which equals c1 times e to the 4x plus c2 times e to the 6x. Before we move on, there is a really huge, crucial part that we have to worry about here. So this, in the lecture slides, is sum of functions. And so what you end up doing is you solve respectively each of the functions themselves, and then you add them together and go on about your life. Okay? So what you have to do is be wary of this 4x. So you see how this is this e to the 4x is repeated here? It's repeated right there. Okay. So with that, what we're going to do is we're going to add the x to this. Okay. And when we end up solving each of the equations separately, okay, and we're suggesting our solutions, then we have to consider that x as an extension of to the 4x, so we don't repeat the same solution. Okay, so the first thing that we're going to do is address the 2x right here. So what I'm going to do is I'm going to say that, okay, I have y double prime, and we're gonna circle back to this in a second, but just bear with me. Minus 10y prime plus 24 equals 2x. My guess here for my particular solution is yp equals ax plus b, yp prime equals ax, and yp double prime equals 0. So plugging that in, then I get 0 minus 10ax plus 24ax plus 24b equals 2x. Let me just check my notes. Yeah, okay, cool. So we're going to factor by grouping. And after I get that, then, or let me just reorganize really quickly. Minus 24ax plus 10a minus 24b equals 0. Factor by grouping. Then we get 2 minus 24a. And we have this. You can factor out 1, but we're just going to leave that as is. Okay. So if this x equals 2, right? But we have it in the equation that we already isolated for 0. So we're going to set that 2 minus 24a equals 0. I feel like every time I click that button, it just doesn't want to work with me. Okay, cool. So we have a equals 1 over 12. Okay. And following that, we have 24b equals 10a. And I have it already figured out. So the answer to this one is 5 over 144. Cool. So those are the coefficients for my first one. Now for my second one, where my guess is yp2 equals c times x e to the 4x. And what you could say are to the totality of our guess was at the beginning was that in the initial because I got a chance to finally read through the initial solution to this. When we originally do this, the first thing that I fucked up, because I got this on my second try, was that when you're guessing when you do your complementary solution, and you don't consider the extra x here in your complementary, okay? You account for that in the particular solution that you guess. And the particular solution that we guess with respect to each term, and I'll write this down in black here, is 1 particular equals ax plus b plus cx e to the 4x. This is the totality of it, and we split it up into, you know, y1p or yp1 and then yp2. Okay, and so we take the derivative of yp2 prime equals ce to the 4x plus c4 e to the 4x. Yp2 double prime equals 4 times ce to the 4x plus c times 4e to the 4x plus c times 16e to the 4x. Cool. Now, we shove that back into our characteristic equation, and we're going to get, and I'm just going to copy and paste this to make life easier. We're going to get this as our first function, okay? And then we're going to have, where this is where we're going to continue off, minus 10 times c times e to the 4x minus 40x times c times e to the 4x. And then we have plus 24 times cx e to the 4x equals e to the 4x. Cool. Because this is the original part of the function that we're looking for. Okay, so you'll see that we have, look at the x first off. We have x, okay, we have x, and then we have, just writing in the x when I distributed it, we have an x right there as well. So 16, 40, 24, all with x. They cancel each other out, okay? And then following that, we have all of these are just by themselves. And so we have really negative 2 times ce to the 4x equals e to the 4x. And it doesn't take a genius to see that 1 over 2, negative 1 over 2 equals our solution. Or sorry, our c value. And so after that, what we end up doing is, and then I'll continue this off just so we have a full map out, is that we start plugging our values. Why is my iPad really slow when it does that? Okay, so we end up plugging our values. So we get something like y equals 1 over 12x plus 5 over 144 minus 1 over 2x e to the 4x plus c1 times e to the 4x plus c2 times e to the 6x. Okay. And now, with our initial value that we have right here, we are going to solve for the c's, as always. And so, taking our first derivative, or sorry, not taking our first derivative, just plugging in the first value, we have y equals 0, 5 over 144 plus c1 plus c2, and c1 equals negative 5 over 144 minus c2. I organized that just so we can get back to it. Y prime equals 1 over 12 minus 2x e to the 4x minus 1 over 2 e to the 4x plus 4c1 e to the 4x plus 6c2 e to the 4x. Then we get 4 after we plug it in, right? Equals 1 over 12 minus 1 over 2 plus 4c1 plus 6c2. Okay. And then continuing on, we kind of bring all of these terms over. We're going to get 53 over 12 equals 4. Okay, yeah, I see what happens here. Equals 4 c1 plus 6 c2. Okay, and then we're going to expand the c1 in. Okay, so we're going to get 4 times negative 5 over 144 minus 4c2 plus 6c2. Okay, right? And then continuing, kind of isolating for c2, we're going to get c2 equals 41 over 18. And you can move over and rearrange as necessary. Right? Because we're going to bring these terms over and then add up these to get 2, right? And then we're just going to divide the 2. and that's it. And then we get, just see if I rewrote it out in its entirety somewhere. Basically, you get C2, right? And you're just plugging in C2 and C1 into their respective places, and then that is question 9. All right, this question took me, I God knows how many pages, but I did so much work on it, and I couldn't end up getting down to the solution, which is fine. However, I don't know if I want to take up, like, I have 6 pages of work that I did for this, via variation of parameters. So we're going to probably leave it right there. I will probably end up posting short video for this when I figure it out. And then, what's it called? I feel like there was something else I wanted to do. Yeah, we'll just let me know if you guys want test 1 review. Like, I don't know if I should go back over that. And then also let me know if you guys want like a different background. Like or also like the solutions, like how many tries it takes me on a question. Just let me know if you guys want that. That way I know if I should or shouldn't kind of go into the full kind of depth of the test. But yeah, hopefully everything makes sense, and if anything doesn't, as always, feel free to reach out. Okay guys, take it easy.